Okay, good morning. Any questions? Any comments about what we are doing? Okay, so we'll continue putting in more and more particles into more and more non-interacting particles into single particle states and see how things develop. So particles that are not interacting with one another, so very many particles not interacting with one another, we interpret them, okay, we call them gases. So what I'll discuss those under the name of quantum gases. So there will basically be two types of quantum gases, fermions and bosons. Okay, in fermions we'll basically look at spin 1 half particles, so a good model of electrons. For bosons we'll look at perhaps bosons with mass and photons separately. Okay, so suppose I have a box, okay, I'll take it to be a cubic box for simplicity in algebra, L, L, L. So, and I start putting in particles. Okay, so we know what the wave functions look like. Okay, so the wave functions have to go to 0 at various ends. So if I just call this, for example, the z-axis, x and the y-axis, the wave functions go like sine, okay, kx x times sine ky y and sine kz z. And the boundary conditions indicate that this kx is going to be some integer, let's call it an x, pi or L. Similarly for ky and kz, so ky is going to be ny pi or L, and kz is going to be nz pi over L. Okay, so if we now try to represent these values in a set of coordinates which correspond to the k values, so we'll call this the k space. Okay, so k space is this inverse length, okay, space. I have these variables kx, ky, and kz. And you see they can get only discrete values. Okay, so depending on what an x is, or an y is, and nz is, you are going to get these possible discrete values, right? So any state in the box can be represented by some kx, okay, some ky, and then I go up to a certain value of kz, right? So this point here is going to be kx, ky, kz, and the possible values that this kx, ky, and kz can take are discretized in this pieces of pi over L. So this distance between these mesh points, okay, the available k points are given, okay, in multiples of pi over L. So since L is going to be something macroscopic, okay, so let's say set of particles in a box, so L is quite large, so you can approximate that as a continuum, but you have to be careful because you are going to also put large number of particles into it. So you also keep track of the counting. Okay, so which particle goes where. Okay, so I have a structure like this, and now what will happen as I put more and more particles into this box? Let me look at lowest energy states. Okay, so we have to specify what type of particles we have at this point, but let's just assume, okay, for as a start, let's assume that we have electrons, okay, electrons in a box. So if they are electrons, they will be spin 1 half particles. So I have to be careful in placing these things in these states. I cannot put any more than 2 particles in the same energy state. Okay, 2, because then I can put the spins in the singlet state. So 2 spin states per each dot that I put inside, okay, this space. So wherever I look, okay, I'm going to get a possible state, and I can put up to 2 particles. So how do these things fill up? Well, I start with the lowest energies, and I fill all of these states as I put more and more particles into it. Okay, but how do I keep track of the energies? Now the energy is going to be h bar squared kx squared plus ky squared plus kz squared over 2m, right? So all particles that have the same kx squared, ky squared plus kz squared have the same energy. So what does that correspond to geometrically?
A sphere.
Okay, it will be a sphere, right? So all particles, okay, that are on a spherical surface. So let me just show it like this. You see, the way I constructed this, all of these nx, okay, ny and nz have to be greater than 0. Okay, so I have actually only this positive kx, positive ky, and positive kz part of the state. Okay? So any point here that has all points that are on the spherical surface have the same energy. Now let me do some state counting. Okay, so as we said, L is quite large. Okay, so if it's small, then obviously you have something like a quantum dot, and you can look at each one of these states individually. But if you have a big box, then these L's are very close to one another, and I can start approximating various sums with integrals. And in order to do that, for example, if I want to count the number of points that I have inside a certain energy, okay, or all particles that have an energy less than a certain energy, for example, what do? I need all the points inside that spherical surface. Okay, so what I do is I go and choose a small spherical shell here. Okay, it's actually 1/8 of a sphere. Okay, so I have something like this which extends all the way around. So it is a shell which has radius k. Okay, so this k I define in terms of these kx squareds. K is kx squared plus ky squared plus kz squared. Okay, so the number of, okay, so let's first look at the volume of that. Okay, so volume of, okay, sphere, actually sphere over 8, right? Because I'm just looking at the positive stuff. Between K and K plus dk. So how much will that volume be? Well, if it were a full sphere, I would get 4 pi k squared, which is the surface area of the full sphere, multiplied by dk, right? So I have 1/8 of that. So that's that. Now, I want to find out how many points there are in a certain volume here. So the easiest way is to consider the volume of a small cube here. Okay, so if I take a cube here, which is going to have dimensions pi over L cubed. Okay, so that's the volume of a small cube, and there's 1 dot per cube. Okay, simple cubic lattice. You can associate 1 dot with each one of these cubes. So this is the volume that I am considering. If I divide that by this, I get the number of points. Okay, so number of energy states, okay, within, okay, let me keep calling it sphere, well, spherical shell, spherical shell divided by 8, okay, is going to be, okay, 4 pi k squared dk, okay, divided by 8, and then I divide that by the volume of a simple single cube, pi over L cubed. Okay, so I have that many energy states with a k number between k and k plus dk. Okay? Now, since each one of these can take 2 electrons, I just multiply it by 2. Okay? So that's because I can put 2 electrons into the same energy state. All right? So that means if I multiply by 2, this part is that number of energy states with that. If I now multiply it with 2 as well, then it gives me number of electron states, okay, within the shell. Okay, so this factor here is called spin degeneracy. What we are just saying is that there are 2 spins that you can put there with the same energy. So same energy, 2 states. Okay, so there's a 2 factor of 2 spin degeneracy. Okay. All right. Now, let's then find the total number of states that you have up to a certain value of k. So let's again remember what we are trying to do. We are putting in electrons one by one into the lowest energy states, right? So as we put particles into the lowest energy states, they start to fill up. And they start to fill up in such a way that they fill, okay, these spherical structures in this K space, Kx, Ky, Kz, okay? So up to a certain energy, and then once all of those energy levels are filled, now they have to go to a higher K value and fill out that part of that spherical shell. Then they go out, okay, and fill out another spherical shell, and so on. So this is something that we are looking at, the lowest energy of the system. Obviously, there are excited energy states here, etc., but we are looking at only the lowest energy states. So if you like, something that happens at zero temperature. Okay, so once I put in n electrons into this system, okay, so I have n electrons. If I put n electrons into this, I am going to fill a, okay, 1/8 of a sphere up to a certain radius, okay, of K. So that K is called the Fermi wave number, the K value for F. So that means, okay, if I want the ground state, okay, this says all states with K less than or equal to Kf are filled, okay, and others are empty. So that's the lowest energy of this Fermi gas, okay? So all of the electrons are in the lowest energy states. They fill up all these states up to, excuse me, Kf. All right, so how many such, okay, how can I relate this to that quantity? Well, this just says that if I just integrate this, so let's see what this is. There's an 8 in the numerator, 8 in the denominator. So no numerical factors, but there is an L cubed in the numerator and a pi squared down below. Okay, and then I have K squared dk. So if I integrate, now if I add all of these states, okay, in these shells from 0 to Kf, okay, I'm going to get a result, okay, so that is going to be equal to the total number of particles that I have in the system. Okay, so L cubed I'm going to replace with the volume of the system. Okay, so L cubed is just the volume of the system. So somehow the result should be independent of the geometry, okay, details of the geometry. So if you have sufficient patience and need exercise, do this for a spherical box, okay, and see what you get. Okay, so what we are going to get is the volume, excuse me, over pi squared of K F cubed over 3 is equal to n. So this Fermi wave number is going to be related to the density. Okay, so let's just work out the algebra. So Kf is going to be equal to 3n over v pi squared cube root. Okay, so n over v. So what is n over v? You can either look at it as a number of particles per unit volume, okay, or you could also look at it as volume divided by n, okay, in the denominator. So that's the volume per particle inside the system, and you take its cube root. So it's something like interparticle spacing, Okay, obviously there's the factors 3 and pi and whatever. Okay, but okay, so if you take pi to be approximately equal to 3, okay, so this is 3 cube, so it comes out of the cube root as 3. So it's the kf becomes something like the volume per particle divided by, volume per particle cube root. So that gives you 1 over distance, which are the units of k. And then you have a factor 3, which is sort of correcting it. Okay, so that gives you an idea about what kf is. So if you have even a macroscopic object, okay, and you have approximately, okay, 1 electron per atom inside this object. So atoms are spaced approximately few angstroms apart. So that means this kf is of the order of 1 over angstroms. Okay, so that gives you an idea about what the scale of kf is. Now, this of course corresponds to an energy, as we had over here. So the energy is called the Fermi energy. So EF, the Fermi energy, is going to be h bar squared kf squared over 2m. So it's going to be h bar squared over 2m times this kf squared, which is 3n over v pi squared, okay, 2 over 3. Okay, so these are the parameters that sort of relate the particle density to the energetics of the system. Okay, we can do a little bit more. You see only the electrons at the top of this energy scale have energy EF. Those that are inside, okay, with very small energies, of course they have much lower energies. So I want to find the internal energy. How do I find the internal energy? Well, I just use my, okay, so if I just now look at that plot again. So again, I'm just going to go to a certain k, okay, and take a thin shell so that its thickness is dk. So I know how many points there are in this interval, but I also know their energies. Okay, so inside this shell, the energy of the particle is h bar squared k squared over 2m. So I'm just going to add them up. Okay, so the internal energy is going to be equal to, okay, the number of points that I have in that interval, which is given right there. Okay, so let's just put that down. So that's going to be what? 1 over pi squared. There's a volume factor, right? There's V. And where did I write that? V over, okay, pi squared k squared dk. Okay, so these are the number of points. You see, this is the unitless. V has units of distance cube. K cubed has units of 1 over distance cube. So this is unitless. This is the number of points between k and dk, k plus dk. Okay, now I multiply this by the energy of any one of those states, okay, inside that interval, and I integrate it from 0 to kf, because those are the states which are full. So let's go through that algebra. Okay, so I'm going to get V over pi squared times h bar squared over 2m. And then I have k to the 4 dk 0 to kf. Okay, so this gives me k to the 5 over 5. So I end up with v over pi squared h bar squared 10m because of the 1 over 5 factor. And then I have kf to the 5. Okay, so let's put in that kf to the 5 into the equation. So the internal energy becomes equal to, okay, let me just rearrange terms here, h bar squared v times h bar squared over 10 pi squared mass of the particle. Now kf to the 5 to the 5th power. So kf is 3n over v okay, times pi squared, okay, to 1/3, so it's going to be 5 over 3. Okay, so you can obviously simplify this a little bit, but okay, you see that this is the you no longer have a simple relationship between particle density and the internal energy. Okay, that's the total internal energy of the system. And let's just look at, for example, the volume dependence, because from that we can again obtain some microscopic relations. You see, if you look at the volume dependence, so this is equal to something, okay, some number times v times v to the minus 5 over 3, right? Because it's in the denominator here. So that's 1, 3 minus that. So it's going to be something, let's check my algebra. So it's 1, 3 minus 5 minus 2 over 3, right? Okay, it's going to be minus 2 over 3 power of the volume times some constant. Okay, so what we can do now is look at the pressure on the walls of this container, because this has some energy, okay, inversely proportional to volume, some power. So if I try to squeeze this system, what will happen? If the volume decreases, I am doing work on the system, which means the energy of the system should increase. Okay, why is that? Because the pi over L, the mesh points in the K space are now going to get closer together. Okay, so the particles will start to move into higher energy states. Okay, yes?
Hocam, why did we define something such as Fermi energy, right? That,
yeah.
Why did we define it, and is it related to total internal energy?
Well, it will turn out that it is related to the total energy. Not directly, but of course, Fermi energy is okay, let me just finish this and then I'll talk about Fermi energy also. Okay, so the internal energy then is going to increase as I push the system in, and just conservation of energy tells us, okay, first law of thermodynamics, right? If you change the volume of the system, the change in the energy is going to give you the pressure. Okay, so the pressure on the surface of the box will be given by that. And what happens if I just differentiate that quantity with respect to V, well, I'm going to get minus 2 over 3, okay, the same dot, 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 but I'm going to get 1 less power of V, right? So what I'm going to get effectively, this will be plus because of this minus sign. So what I'll get is going to be the 2 over 3 times the same thing, V to the minus 2 over 3, but 1 power of V less. So it's going to be 2 over 3 U over V. Okay, so this is interesting because if you just look at the classical gas, classical ideal gas, so let me just squeeze it here, you have the same expression. So we have this PV equals N K Boltzmann T, right? And U is equal to 3 over 2 N K Boltzmann T. So you can see that the pressure is going to be 2 over 3, right? U over V. So it's going to be exactly the same thing. In fact, even at finite temperatures, this still holds not only for the for fermions, also for bosons. So this is something quite standard for the ideal gases, okay, non-interacting particles. Okay, so what is happening here? Particles are at the lowest energy levels, so they fill up all these states up to a certain energy, which we call the Fermi energy. Now, what happens, okay, in practice? First of all, there's some electron-electron interaction, but also there's some temperature, right? Now, the temperature associated with the motion of the electrons actually turns out to be quite small for various practical systems. So let me perhaps discuss it over here. Okay, so I have a sphere here which extends up to this Fermi, okay, Fermi wave number. By the way, this is obviously the momentum is equal to h bar k. So if you multiply this by h bar, you also have the momentum. So this is sometimes just called, okay, loosely Fermi momentum, although Fermi momentum is, of course, this thing multiplied by h bar. Okay, so, but that corresponds to a Fermi energy. So EF is equal to h bar squared kF squared over 2m. Now, the ideal case, all states up to that Fermi level are all full. Okay, so let's try to understand what happens to the electrons if they get a little bit more energy. Suppose I start heating them up. Now, the electrons which are deep inside these levels need a lot of energy, in fact, to move to another state which is empty. So they are stuck, okay? Only the electrons which are near the Fermi surface can get a little bit of energy, use it, and go outside this Fermi sphere. Now, the amount of energy that they can get from the heat around them, okay, so the amount of jump, the amount of energy that they can have thermally is, okay, given by this K Boltzmann times the temperature. Now, in a typical material, in something like, for example, copper, where you have all these free electrons, where this is a very good approximation, Okay, the Fermi energy is of the order of electron volts. Because remember, the inter-electron distance is of the order of angstroms. So their wavelength near this Fermi point is of the order of angstroms. So this EF is of the order of, let me say, few electron volts. So this is actually quite a large amount of energy. Okay, so this KBT at room temperature, so at 300 Kelvin, is about 30 milli electron volts. Okay, and we are 300 Kelvin, we are quite a few Kelvin above zero. So even if you go to something like, okay, so KBT at 3000 Kelvin is going to be 300 milli electron volt. So we are still below 1 electron volt. Okay, so the electrons in copper actually behave as if they are at zero temperature. So the zero temperature limit is actually quite important because most of the objects around us, the Fermi gases that we have in our everyday life, okay, all the metals, conductors, etc., that we have around us, have Fermi energies which are quite high, okay, and because they are quite high, the approximation that all the low energy states are filled and the higher energy states are empty is a very good approximation. Now, what happens when you include the electron-electron interaction? Not really that much, okay? That perturbs this density so that there will be some states full outside the Fermi energy and some that are empty below the Fermi energy due to the electron interaction, but it's not going to change all that much, okay? So this is a very useful picture of what is going on. All right? Any questions? Yes.
Hocam, what does pressure represent in an electron gas system?
Well, okay, so pressure is there, whether it's classical or quantum mechanical system, right? Because there are, okay, a group of astrophysical objects, for example, stars, okay, these white dwarfs, which are in which the electron pressure is an important part of the stability of the star. Okay, so in its center you have this big fermion gas, which is holding the star from collapse. So it's that pressure. So in that sense, it's just the thermodynamic quantity, macroscopic quantity, that is actually there. Okay, whether it's quantum or classical.
How about the metal?
Okay, in a metal, of course, the electrons would actually like to fly apart because of this pressure, but the protons are holding them back. Okay, so. Okay, one point about counting these states. You see we have the count over here, but usually you'll see in many places, instead of working with this 1/8 of a sphere, what you do is you use periodic boundary conditions. This is a okay, so this is a tool which is actually quite useful in practice, and in various problems where you don't want any boundary effects, it is in fact useful in other ways also. Okay, so now in this case I have this box again. Suppose I have the same box, but this time I'm putting dotted lines here, which means that I don't have infinite walls anymore. So it's again an L by L by L box. Okay, but in this case, I have any particle that comes in from this side and goes out immediately enters at the other side. Okay, so things like the wave function, for example, psi x plus L is going to be equal to psi at L, which means that these wave functions, these are free particles now, remember? It must, yes.
Psi at x, right?
Psi x, thank you. So this psi of x must have a form, so let me say just proportional to e to the I 2 pi over L times n. Okay, and the larger the n, obviously, the larger the energy. So I can write this as e to the I 2 pi, well, I'm sorry, I k, I forgot the x. Okay, let's rewrite this. E to 2 pi n x, which is equal to e to the I kx x. Okay, so that's the x direction. Now the kx here, you see, is going to have some bigger interval. So previously our mesh was, so let me put this mesh over here again. So now our k space looks something like this: kx, ky, and kz. Okay, and a single origin. Okay, so, and over here now I have a mesh which is now bigger in all directions. In fact, it's twice as big as the previous one. But now this can extend in plus or minus directions. Okay, so let's see what happens. Any point here now, as before, I go to a certain kx, where am I? Ky, and then go up to a certain kz. So this is again my point kx, ky, kz, as before, except that the mesh now is twice what it was before, 2 pi over L. But the difference from the previous case is now negative k is also allowed because those correspond to particles going towards the left. Okay? So now if I want to make the same calculation as before, suppose I take a sphere now, because this will go in both directions, and take again a small shell. Okay, so its thickness is dk, the radius is k. So what is the volume of that? Well, this is all the volume. So the volume here is going to be equal to 4 pi k squared dk, right? I divide that by volume per state. Volume per state is still, okay, it's 2 pi over L now, right? The cubes that we are constructing now are twice the size as before. So these cubes that I have here, okay, so this thing here is 2 pi over L cubed volume. So if I divide this volume by that volume, I get the number of points. okay, times the spin degeneracy. Okay, so this is the spin degeneracy. But you see, when I calculate this, I get exactly the same thing. I get, okay, again, the 8's cancel. I get k squared dk over pi squared times volume. Okay, so wherever that is, right over here. Okay, so you see, I get the same factor as before. So you can do your calculations any way you like. You can either use periodic boundary conditions, okay, or actually use a box with infinite potential on the outside. So you are going to get exactly the same results, because in both cases you are looking at particles which are really confined to a certain volume. Okay, they cannot escape this volume because as soon as they get out, they get in at the other end. Okay, so it doesn't matter whether you have a box with hard walls or just periodic boundary conditions. So this usually gives you a little simpler algebra for other problems, mainly because you don't have a surface here. Okay, so in the other case you have a surface near the edge of the substance. Sometimes you are interested in what's happening near the surface, then of course you have to use some other model. But if you are not interested in what's happening near the surface and what's going on around the bulk, that's what you do. Okay, let's have our break now, and then we'll continue. I keep forgetting this, so please pass this on.